Welcome to the 19th part of Spring Boot with Kubernetes tutorial series. In this video, we are going to talk about what is Docker and what is Kubernetes, and we are going to see how we can set up cluster using kind. So what is Docker? So Docker is a containerization technology to package and distribute applications. What does this mean? You may be building your application using Java, Python, PHP, whatever the tech stack you choose, you build the application. And then if you want to distribute using Docker, it's kind of a standardized process, like you create a Docker image from your application artifact, be it jar or DLL, whatever, and then you can share it with other people as a Docker image. So all they need to have is installed Docker up and running. That's all they need to have. Then they can pull your Docker image and then run the application. Whereas without Docker, it would be much more tedious process. So what kind of a problems Docker is trying to solve? Okay, so we all know at some point of time in your career, you might say it's working fine on my machine, right? So you build an application, you test it on your local laptop, and then you share it with other team members, maybe QA or some other team, and they are saying that it's not working. When I try to run, it is failing. So then you had to go and debug, are you using the same version of software? Maybe if you are using Java, you might have to check, are you using the same JDK, and are there any settings differences? So all these things happen. Whereas with Docker image, like you build the application, you create a jar file or war file, whatever is the packaging technology you use, and then you create a Docker image out of your artifact and you share it with the other team members. They don't have to install Java or any other things because they are already part of the Docker image, and whatever the JDK that you choose to build, which also working fine, is going to be part of the Docker image itself. So all the other team needs to have is Docker installed up and running, and they need to have the access to this Docker registry where you put the Docker image, and they can simply pull the image and then run it. So it minimizes this it works on my machine problem to a great extent. Then how do we build a Docker image? So in our previous videos, we have seen how to build a Docker image from Spring Boot application, and also we created a Docker image from our Next.js application. So a typical process would be to write a Docker file, which is nothing but a series of steps to specify how to create a Docker image. So here, usually we take some base image. In our case, let's say we are trying to build a Docker image from a Spring Boot application, right? So we are taking a base Java image. Here I am taking 17, and then I am adding my application jar file into some location here inside the Docker image, and this is my source jar file location. And I am trying to say when we start the application, we want to expose this port 8080, and then this entry point is nothing but the command that we want to run when somebody wants to spin up a container from this Docker image. So we are starting java -jar and the location of the jar file. Okay, so these are nothing but steps. We can call it as a recipe to create our Docker image. And if you are building some Python based application, instead of instead of this base Java image, you would take some Python image. Similarly, for whatever application you are building, you choose one of the base image and then add your application artifacts, and then in some entry point you start the application, right? And this is the usual process to create a Docker image. In addition to this, there are few other mechanisms, and depending on the tech stack you are using, you could also use, let's say, build packs, where you don't have to write the Docker file. Depending on the tech stack and features you are using, it also automatically pulls in required dependencies and build the Docker image. Similarly, there is a zip plugin, which we have already covered all these details in our Spring Boot Kubernetes tutorial series, part 7. how to build a Docker image from Spring Boot application. So you can also use zip plugin and then build the Docker image without having to write Docker file. Okay. Okay, then there are kind of terminologies like Docker image and container. So what is what? So for easier understanding, I would say if you think of Docker image as a class, then container is an instance object of that class. Okay, so once you create a class, which is nothing but a blueprint, right? And then you instantiate as many objects as you want from that class. So in the same way, you can create a Docker file and then you can run this command docker build and minus tag. You are giving a name to your Docker image and specifying the location where to find the Docker file. Okay, then it's going to create a Docker image with this name. From that, you can create as many containers as you want. Here we are saying Docker run and giving a name to the container as app1 and mapping the ports and then specifying what is the image name. And then we are running another command, creating another container from the same image, and this time giving the name as app2. So this way, once you create a Docker image, you can create any number of containers and then you can manage each container separately. You can run this and then you can stop it, pause it and restart it or destroy it. And this doesn't affect the second container. Okay, you can independently manage as many containers as you want. So one thing to note is these containers, once you spin up a container and then run the application for a while, and then if you stop it or destroy it, the data that is stored inside that container is gone. There is no getting back once you destroy this container. So usually if your application is a complete stateless application, like you build a REST API and which performs some calculation and then return, it's not a problem. Like even if you destroy this container, you can spin up another container if you need. But let's assume our application is also doing some file manipulation. Like when you get a request, you do some calculation and then you create a file and store it into the container. And then after a while, if you destroy that container, all your data is also gone. Okay, and we don't want that. And another scenario is, what about running the containers like database, Postgres or MySQL, whatever. So here, as you run the container and then you store the data, by default it's going to store all that data inside the container. But usually you don't want to lose the data, right? You want to always make it persistence. Even if you delete it and then recreate another container, you want to have the data persisted somewhere. So to handle that scenario, we would use Docker volumes. So there are multiple ways of how we can handle volume creation. So the first one would be you can create a Docker volume here, and then while starting your container, you can map that volume into some logical path into the container, and within your application you can write data to this location, which obviously stores into this volume. And usually these volumes don't get destroyed when you destroy this container. And if you want to explicitly delete that volume, you can delete it. But by default, if you destroy this container, it won't destroy this volume. And these volumes, you can store it into your file system, or you can use some cloud storage so that it won't be accidentally deleted. And another common technique that is used, especially during development, is you can map one of your host file system path into the container, which means in your local file system you have some folder and some files, and you want to make them available within the container itself. So you can use volume bind mapping like this. You can put the path, host path, and then what is the container path you want to map to, and then start the container. So this way you can access these files within your container from the application. Okay, also if you write any files or change any files in this directory, they are going to reflect in this host directory as well. So how do we, once we build the image, how do we share it with other teams? Like there are various Docker image registries available. Let's say if you are building a public open source project and you build your application and then you create a Docker image out of it, and then you can publish it to Docker Hub and make it available for anybody. In the same way, there are other registries available like Quay, which is from Red Hat. And if you are using AWS, there is Amazon ECR where you can push your images and make it available only for the people that have access to it. And similarly, Google offers Google Container Registry, Microsoft Azure offers Azure Container Registry. So you can securely store and share with only the people you want to share. So far we have talked about creating a Docker image and then running it as many containers as we want. But usually in our applications, use other dependencies as well. Let's take our own Spring Boot application, a bookmarker, which is using a database, right? So when we start our application as a container, it needs another container to talk to, database container, but they need to be in the same network so that they should be able to communicate with each other. If you use Docker only without Docker Compose, you need to specify and link them using a bit of difficult commands using hyphen link or something like that, which is very tedious. So that's where Docker Compose come in, and it really simplifies running multi-container applications. For example, you are building an application which is using some Postgres database and also using Redis as a cache server. So if you are not using Docker Compose, you would be running multiple commands to start your application. You start your Postgres and Redis. So it's kind of a very tedious process. Whereas with Docker Compose, you can define in this docker-compose.yaml file, specify all the services. Okay, you want to use a database and the image is Postgres, and you want to use a cache server using Redis and your own application, and you can specify depending on DB and cache. So when you start Docker Compose up, it's going to pull the images if they are not already available and then spin up all these containers. And you can, by default, if you don't specify, all of them run in the same network so that they can discover each other. Okay, so Docker Compose really simplifies working with multi-container applications. You can pretty much run your applications using Docker very easily, and then the best part is during development you can spin up your whole platform using Docker Compose, and then once you are done you can destroy and then recreate very easily. It's not a tedious process like earlier. Okay, install that, install this, and configure this and that. So there is no such a tedious process anymore. This is fine for local development process, but how about running our containerized applications in production? Let's say we build an application and we run using Docker and Docker Compose locally. And for any reason, if one of our application hangs due to resource limits, or we don't have more memory, or any other issue, like, or maybe there is a bug in our application and it throws out of memory exception, something like that. So it's gonna stop and you wonder why it's not running, and then you have to debug and then restart or whatever you need to do. But that is fine for development purpose, but in production that's not something you want to experience, right? You usually want to always run n instances of your application, and there shouldn't be any downtime. So even if there is an issue with one of your container, you want it to be terminated and restart another container automatically. Also, you might want to spin up more containers or spin down some containers depending on the load of your application. So maybe if you have a predictable load, you would like to have 10 containers running from some time to some time. But you also know that during night time there won't be much traffic, so you want to automatically reduce a number of containers running to a minimum. Or depending on the load, dynamically you want to spin up more containers. So all these things doesn't work with plain Docker. Maybe you can write some scripts and all, but that would be very tedious to manage. So this is where we want some container orchestration technology. So one of the most popular container orchestration platform is Kubernetes. That's where Kubernetes come in. So what is Kubernetes? Kubernetes is a container orchestration platform. Once you create a Docker image from your application and you want to run it in a production with high availability and scalability, Kubernetes helps to achieve this high availability and scalability. When you schedule a Dockerized workload to run on Kubernetes platform, you can easily scale up and down based on your needs. Maybe you want to run n number of instances of your service. So in Kubernetes, it is very easy to scale up and down your number of instances. And also, for any reason, if one of your service instance goes down, Kubernetes ensures that it will always run desired number of instances. So Kubernetes takes care of a lot of such activities to reconcile and then verify how many instances that you want to run and how many instances it is currently running, and then make sure the desired number of instances are running, either by terminating the more number of instances or recreating more number of instances if required. Let us take a look at what are the components in Kubernetes. So if we go to Kubernetes documentation, we can see this diagram where it represents what are the various components that are available in a typical Kubernetes cluster. So there can be one or more master node, which is also called control plane, and there are n number of worker nodes. And here we have etcd, which is to store entire cluster information. And whenever we schedule any Dockerized workload, it will take a look at which node can take up this work and then allocate that particular task to one of the available nodes. And each node contains a kubelet process to communicate with the master node so that it gathers information of each and every node, so that it is capable of understanding whenever we ask to run any Dockerized workload, it has all the information about each worker node, and then find out which node is capable of running this particular task and then allocate it on that particular node. Quick look at what are the key objects that we use in Kubernetes. A pod is nothing but a smallest deployable unit in Kubernetes world. A pod encapsulates one or more containers, but most of the times it is one container. But there are cases where you want to use sidecar pattern. In that cases, there can be more containers as part of one pod. A replica set is ensures n number of desired number of instances running always. By any reason, if one of the pod dies, it makes sure that to create new containers to meet the desired number of instances requirement. On top of it, there is deployments which uses replica sets under the hood to make sure a number of instances running, and also keeps track of all the rollout history, which means first assume you deploy version 1 of your service, and then you upgrade to newer version 2, and later you figured out there was some issues with version 2 and you want to roll back to previous version. So using deployments, you can do that. And then while using replica sets and deployments, there can be n number of instances of your service running, but you need to expose a logical name to the external world so that they can communicate with your service without requiring to know which pod to talk to, because the pods are ephemeral, which means they can come into live and then they can get destroyed. So you shouldn't be relying upon pods directly, pod IP addresses or anything like that. So this service exposes a logical name like a URL DNS name like that, so that it will always be reachable irrespective of any number of pods running. So we don't care about the number of pods, and our clients always talks through via services. And in any for any typical service, there will be some level of configuration required. So there is config maps and secrets that we can use to provide the configuration data to our service. uh, Typically config maps are used to provide non-sensitive data, whereas secrets are used to provide sensitive data like passwords, API keys, things like that. But be aware that secrets here is nothing but simple base 64 encoded strings, which are not really secure. And when you are using secrets, you need to take additional security measures like applying role-based access controls and encryption at rest, things like that. And also, while using any stateful services like database or things like that, you don't want to lose the data. So in that case, just like how Docker uses volumes, we can use persistence volume here, so that even if pod dies, these persistence volumes be persisted, and then even if a new pod restarts, it will still use the same data that it has earlier. And you can create persistence volumes leveraging any of the drivers, like you may be running your Kubernetes cluster on AWS, then you can use EFS or EBS volumes as a persistence volume drivers. And when you are running any pod and you want to have some volume mapped to your service, then you need to claim it by using persistence volume claim. So basically, using persistence volumes, you can create volumes, and then using these claims, you can claim for a persistence volume, which Kubernetes cluster figures out which persistence volume is available for your requirement, and then attaches to your pod. And then finally, there is ingress controller. Let's say you are building a whole bunch of microservices, and you want to give logical names like api.bookmarks.com, something like that. And there will be multiple subdomains also. So you may want to route different DNS names or different subpaths to a different services. Using ingress controller, you can route the traffic to one of these services based on host name or URL patterns, things like that. So these are the key services that most of the applications use. So we are going to see how we use all these features for our bookmarking application. Next, how do we use Kubernetes? Typically, when in production or in any environments, if you are in cloud, you can use either AWS, GCP, Azure, DigitalOcean, or whatever the cloud platform you are using. Most likely provides Kubernetes platform. You can use that. But for our local development, we can spin up a local Kubernetes cluster using some of the tools available, like a couple of very popular choices are Minikube and Kind. And also there are a few others like K3s and Rancher, things like that. But most of the people are familiar with Kind and Minikube. So we are going to use Kind, and let us see how we can install that. Okay. So Kind cluster installation. So if you go to Kind homepage, kind.sigs.kubernetes.io. I'll share this link in the description. So if you go to quick start, here you can see, depending on your operating system, you can install Kind. As I am using macOS, I will be installing using ru install Kind. Once you install Kind, creating a cluster is very simple. We can simply run Kind create cluster. By default, if you don't give any name, it's going to take as Kind. But we can give a specific name with this hyphen hyphen name parameter. Okay, this will create a simple kind cluster. But we can create any number of clusters. We can create multiple clusters. By default, it is going to create with one node, but we can create with multiple worker nodes as well. Multiple worker nodes and control plane nodes as well. And also you can switch between the clusters using this kubectl cluster info. And forgot to inform, before using Kubernetes cluster, we need to install kubectl, which is again, you can Google for kubectl installation, and depending on your operating system, you can install accordingly. And if you want to delete any existing cluster, you can use kind delete cluster. And if you want to delete a specific cluster, you can pass the name. And also you can create a file, config file like this, with the configuration of okay, we want to have one control plane node and two worker nodes. So we can have a YAML configuration file like this, and then specify kind create cluster and specifying the configuration file like this. So it will create one master node and two worker nodes. And even you can have multiple master nodes and multiple worker nodes also, but for our purpose, we'll have only one node. That is sufficient for our work. And also you might want to expose some of the ports onto your host machine. So what we can do here, we can specify we are going to have one node, and we are binding what is the container port and what is the host port, which means your clusters port 80 is available on your host port 80. Okay, so we are going to use this to expose some of the services onto your host. Okay, and also, as we are going to use ingress controller, we need to see how to install ingress as well. The installation of ingress controller is up to the Kubernetes administrators, because there are multiple choices for installing what implementation of ingress controller you want to use. So one of the most popular one is ingress nginx. So here you can see there is a prepared YAML definitions. It will take care of installing the nginx ingress controller. And here there is a command to ensure this got installed and all the components are ready. So we can use this command to wait for it to be ready. So there are a few steps that we need to perform to install kind cluster. So instead of doing it manually, I have a shell script which takes care of running all these commands and then ensuring it is ready to use. So here what we are doing, once we install kind, then we can call kind create cluster and specifying this configuration file, kind config, which contains the same thing. We have only one control plane node, and we have these mappings. Nodes port 80 is exposed on host 80 and also 443. So both of these are available on our host also. Okay. And here we are running the same command to install nginx controller. Okay, we are running the same command, and then we are waiting for nginx ingress to be ready by sleeping some time, and then running this command to wait out with a timeout of 180 seconds. Okay, so this is nothing but the same command here. And once it is ready, we are just displaying your cluster is ready to use. And because we gave our cluster name SP Kubernetes series, there is another utility called destroy cluster, and here we are saying kind delete cluster and passing the same cluster name here. Okay, so these are the two shell scripts available, so that we can go here and cd into kind directory, and I can run create cluster command. So when you run it for the first time, it's gonna take a little time to download the required dependencies and then start the cluster. Now the cluster is ready, and to verify, it also set the default context to this new cluster. So we can right away start using this kubectl. So we can write kubectl get pods. Okay, currently there are no pods running in the default namespace, so we are good to go. The next tool I would like to install is called Lens, which is nothing but a GUI tool for our Kubernetes cluster. So here, if you go to Lens, K8s lens.dev, you can download installer based on your operating system, and then once you install, you can start the application and you will get this interface. And if you click on this browse cluster in catalog, here it will show all the cluster that are there on your system. So right now we have only one cluster, kind SB Kubernetes series. So when I click on it, it connects to it, but right now there are no workloads running. So this tool becomes really helpful to take a look at what are the pods running, what are the deployments running, or is there any issues. So you can get all that information from command line also, but this is really easy for development time.